Hello everybody and welcome back. In this lecture we will create and train the classifier on the chest X-ray dataset to classify whether an image shows signs of pneumonia or not. I have already imported all the necessary libraries including Torch and Torch Vision to create the model and the data loader, Transform from Torch Vision for data augmentation and normalization, Torch Metrics for easy metric computation, of course PyTorch Lightning, which handles the complete training phase for us, a model checkpoint callback to frequently store the current weights, and a TensorBoard logger to enable logging in TensorBoard. TQDM to get a progress bar when validating the model, NumPy to load our pre-processed X-ray images stored in the NPI format, and last but not least Matplotlib to visualize some results. At first we create our train and validation dataset. As mentioned in the introductory lecture, we can leverage the dataset folder class from Torch Vision. It allows to simply pass a root directory and returns a dataset with access to all data within the subfolders of the root directory. This dataset returns the data stored in the subdirectories together with the name of the corresponding subdirectory as the label. We only need to define a loader function which defines how the unique files should be loaded. Additionally, we need to pass a list of the file extensions we want to load to the dataset folder class. In our case, this is simply npy. Finally, we pass the transformation sequence for data augmentation and normalization. Let us at first define the load file function, so we create a function called load_file, which accepts a path as its only argument. This function simply needs to load the file specified by the path and then convert it to flow32 for training. So we can directly return the object returned by numpy.load path and convert that to numpy.float32. Next, we can define our train and validation transforms. At first, we create our variable called train_transforms, which will take the augmentation pipeline for the training dataset. To combine or compose multiple augmentation functions, we use transforms.compose, which accepts a list of multiple transforms. At first, we have to convert the loaded NumPy array to a Torch tensor. To achieve this, we can use transforms.toTensor. Next, we need to normalize our images by using transforms.normalize. This function accepts our pre-computed mean and standard deviation as the first and second argument respectively. Finally, we can define our data augmentation pipeline. At first, we use random_affine, which allows to rotate, translate and scale the image. So we call transforms.random_affine, define the tuple for the random rotation, which is called degrees, and pass -5 and 5, as we want to have random rotations between -5 and 5 degrees. Second, we pass translate equals to 0 and 0.05, which creates random translations of at max 5%. And finally, we pass scale from 0.9 to 1.1, which randomly scales the image in the interval of 0.9 to 1.1. The last augmentation we use are random resized crops. They crop a random portion of the image and then resize this crop to the desired size. We can access them by calling transforms.randomResizeDCrop and pass our desired image shape. In our case, as we don't want the size of the images to change, we simply pass 224 by 224. It is crucial that we don't crop away parts of the image which show pneumonia, as otherwise we would have to change our label. Therefore, we need to make sure that our crops contain enough information. We can define the sizes our crops are allowed to have by using the scale argument. The scale argument expects a tuple where the first element corresponds to the smallest crop size and the second one to the largest. A crop which contains at least 35% of the image should be large enough to not crop away any relevant parts. Additionally, we of course also want to feed images that are not cropped at all, and therefore we use 1 as the upper bound. Next, we define our validation transforms. Let's call the variable val_transforms and again use transforms.compose. We don't want to apply test time augmentation, so we only use transforms.toTensor and transforms.normalize. We can directly copy those two operations from above. Alright, we have successfully defined our transforms objects. Finally, we create the train and validation datasets. At first, we define train_dataset and now use torchvision.datasets.dataset folder, where we pass at first the root directory to our images. In my case, this is simply processed/train. Again, please verify that you use the path style according to your OS. Next, we pass our load file function to the loader argument and also the possible file extensions, in our case npy. Finally, we pass our train transforms pipeline to the transform argument. Alright, now we can simply repeat this procedure for the validation dataset. Let us quickly copy the call from above and replace our train directory with the validation directory and our train transformations with the validation transformations. Now it's time to take a look at some augmented images our train dataset returns. We will use a 2x2 subplot matrix for this. As usual, we define at first our figure and axis objects and call plt.subplots, where we pass the number of rows and columns. Additionally, let's use a figure size of 9 × 9. Now we use the double nested for loop in the range of 2 to get access to all axis objects. Instead of using our loop counter variable, we simply choose a random index by using numpy.random.randint in the range from 0 to 24,000. This simply returns one integer between 0 and 24,000. Now we can use this particular random index to extract an X-ray image and its corresponding label from our train dataset. Last but not least, we use inj to access the current axis object and call .imshow on it to plot the current X-ray image. Please note that the dataset folder class from TorchVision automatically appends a channel dimension in front of all other axes. However, as Matplotlib cannot handle this, we need to get rid of it by simply indexing it. Let's use the bone color map and additionally access the current axis object again to set the label as image title. You can beautifully see the impact of the different augmentations and also that our crop size of 35% wasn't too small. Almost 100% of the lung area can be seen in all images. Perfect. Next, we are going to create our train and validation data loaders. Before doing so, we should at first define the batch size and numworkers our system can handle. In my case, I can use a batch size of 64 and 4 numworkers. Please make sure to set those values according to your system. Next, let us define a variable called train loader, which we assign the data loader from torch.utils.data loader, which gets the train dataset as its first argument, the batch size as the second one, the number of workers as its third, and last but not least, we set shuffle equals to true. Shuffling your training data is really important. Imagine a case where you at first feed 1000 X-ray images that do not show signs of pneumonia to your network. Then the network would simply learn to always predict 0. After that, you feed the next 1000 images to the network, but they all show signs of pneumonia. Then the network would learn to always predict 1. Therefore, it's really important to shuffle your training data. Next, we define our validation loader by simply copying the line from above. We replace train dataset by validation dataset and set shuffle to false. When validating the model, you don't want to shuffle your data in order to get a deterministic evaluation. When tackling a machine learning problem, it is extremely important to get to know your data. In our case, we should check the distribution of the labels to answer the question, how many images actually do show signs of pneumonia? You can use numpy.unique on traindataset.targets, which is the place where all labels are stored, followed by return_counts equals to true to get the distribution of the labels. You can see that there are much more images without pneumonia as there are with pneumonia. Our dataset is imbalanced. Typically, there are 3 ways to handle such an imbalanced dataset. The first possibility is to do nothing. Sometimes this works surprisingly well. Next, you could try using a weighted loss. A weighted loss function assigns a higher loss to a prediction if the model erroneously predicts the negative class. The third one is to use oversampling. When using oversampling, the overall goal is to show the network as many samples from class 1 as from class 0. In this example, we will test to use a weighted loss of 3, as there are roughly 3 times as much images without pneumonia as there are with. Alright, now the data loading routine is complete and we are ready to implement the model.